All right, so let's get started. So today we are very honored to have Professor Sri Narayanam from University of Southern California to give us a talk at the seminar today. His talk is titled Multimodal Machine Intelligence and its Human-Centered Possibilities. So before he gets started, let me briefly give a brief introduction about Sri. Sri is a university professor, is Nikki and Max Nikias Chair in Engineering, and more recently the VP for Presidential Initiative at University of Southern California. He is a full professor affiliated to many departments. He's affiliated to the ECE, the computer science, the linguistic, and many more. Sri is one of the well-known and most well-known researchers in the area of signal processing in general, and more particularly in the speech signal processing. And he has a wide, prolific portfolio for his research, and particularly he focuses on speech recognition, speech sensing, and human-centered sensing, signal processing, and human-centered machine intelligence. Sri has won so many different awards based on his research. He's a fellow of IEEE, a fellow of ACM, and many other academic societies. And more notably, he is a Guggenheim Fellow and a member of European Academy of Sciences and Arts, and have been received many awards for his research education, most notably including the 2024 Edward Mike Clousey Technical Achievement Award from the IEEE Computer Society, 2023 Klaus Shannon Henry Nyquist Technical Achievement Award from the IEEE Signal Processing Society. So without further ado, let's welcome Sri, please.
Thank you so much, Mi. I'm so delighted to be here and have this opportunity to speak to you all. Hello from Los Angeles. It's a little sunny today, although it's been kind of pretty rainy, unusual for Southern California. But happy to spend this morning with all of you. So as Mi pointed out, the work that my lab and I do is very human focused. We are especially interested in human communication, behavior, interaction, and such. And we try to look at it from sort of computational engineering lens, through multimodal sensing, signal processing, machine learning, both to understand human aspects, but also build technologies that can be useful to support their experiences. So that's kind of what we are up to. So in this seminar today, I thought I will share using examples drawn from the work that we've been doing to illustrate the possibilities of this sort of the ecosystem of machine intelligence, especially from a multimodal sense, that can help us toward these purposes. So my lab, as I said, right, focuses on technologies to understand the human condition and build technologies that can support their capabilities and experiences. So as we all know, especially in the last few years where it is even more accelerated than ever that we've experienced, there's lots of converging advances that are going on, both from a technological sort of perspective. When we think about sensing, one of the themes of this particular seminar is IoT. I know we can sense people and their worlds in ways that we never imagined, right? On people in their on devices, in the environment, and so on. The ability to compute both at the edge, on the cloud, at a scale, and not sort of imagined before. Ability to interpret and process data. Again, with amazing sort of capabilities to share data and to actually share data, not only between devices but also with people, right? Again, devices on, with, by people. So, and there's this convergence that's happening, making us think about all kinds of possibilities, especially human-centered applications. There's also something that's more socio-technical that's been going on, and a lot of amazing cross-disciplinary partnerships across, various disciplines in both academic industry settings and across the world, where people are sharing, data, tools, and so on. That's making possible, people exploring societal applications, globally, and that's also very exciting. So this backdrop landscape allows us to think about new ways of helping understand, support, and enhance this human condition experience that I mentioned earlier. So one of the things that if we were to sort of imagine such a possibility, right? It also comes with a lot of challenges, both technical and otherwise, right? How, first of all, can we make this work for everyone in all contexts, right? People, there's a rich variety in who we are, what we do, what we want, where we are, and so on. So as me mentioned earlier, one of the things that we work on a lot is in human communication, using speech, language, nonverbal behavior and all. So I'll just use that as an example to just illustrate this point. So this is just a parent and a child interacting. In the inset, you'll see audio with some signal with some spectral features extracted. Here's on this inset, you'll see they were both the parent and child were wearing a sort of a wrist-worn device that measured many things like heart rate and skin conductance response, electrodermal activity, which gives you an index of the physiological arousal. And you can see how even this simple sort of interaction is how rich. Let me play that.
And then he got stung by bees to be a lion again, to be a regular lion again. Okay.
Good job. So ideas of machine intelligence, right? We think about, right, multimodal machine intelligence, in fact, can help us toward rich understanding this rich interaction. For example, right, speech recognition. First of all, who's talking when, right? Doing speech activity detection and diarization. What are they talking about? Speech recognition, processing the video to saying to look at expressions, joint attention together with physiologics, and starts giving us insights about this, even a simple snippet of an interaction, how rich it is, and how we can start beginning to quantify some of these. I'll touch upon this point about the importance of being able to understand this beyond traditionally doing things like enabling a spoken language interface, right? That's one of the points and examples that I would like to sort of illustrate later on. So a lot of possibilities for understanding human interaction and behavior using these multimodal machine learning techniques, right? This has been one of the important sort of application areas for decades now. So just to dig a little deeper, right? So when you think about like taking this example of human sort of interaction, right? We see that verbal and nonverbal cues provide access to not only intent, what people are trying to sort of convey, but their sort of express emotions and a variety of information about who they are, even their physical and psychological health status, the interaction context, where is this happening, and often these attributes and contexts are very intricately related, right? And so, in fact, what makes it even more challenging and exciting is that the rich diversity and variability along so many dimensions, both within and across people, that make this sort of study computationally more challenging and hence exciting for sort of people who are working in AI these days. It could be things due to individual differences, whether it's age-related differences, differences due to language background, neurodiversity, interaction type, who's involved in these interactions. There's two people interacting, or is a small group? Is it structured? Who are involved? The social register difference. Where is this happening? What kind of sensors are we using to observe, measure? All these things, are lend themselves to this variability and diversity in along so many dimensions. So any technology or machine intelligence thing approaches we are developing should in fact sort of for it to be useful and serving the purpose of supporting the people and their experiences has to be inclusive to create equitable experiences. And so as a result, right, when we think about human-centered machine intelligence, it's often like can simplify into two sort of intertwined goals. One, to understand, analyze, and sort of characterize this variability, due to, say, for example, age-related differences or differences due to sort of cognitive abilities or things such as knowledge of a language, and then, depending on the needs or the purpose of the particular application, the technologies will try to see, well, how can we address, target that particular source of error. We want to know what someone is saying, regardless of who they are or where they are, right? Like that's a classic, question that people have been asking in speech recognition. Or, for example, disassociating neurocognitive differences in presence of factors related to age-dependent variability or sort of biological sex differences in children, say, with autism. So that's an example I'll share a little later, right? So these twin goals are often the, part of this human-centered machine intelligence. And so this is the sort of, has been a perennial endeavor. It's not a new sort of question, but this is the kind of questions that researchers in this field have been working on. And so now I'll kind of, provide at least my take on how I view this human-centered machine intelligence. Basically refers to engineering methods and technologies to understand human trait, state, behavior, and interaction, perhaps in an integrated way, and then translate that into technologies that could potentially support and enhance human experiences. This essentially involves characterizing at some level or other data information about people, from people, and for people, right? Including sort of knowledge about how people perceive and process and use data, right? A lot of times, we people working on, in speech recognition, computer vision, often have used, human annotation and labeling as either starting point for training models or evaluating models and so on, right? So that's one example of this how humans influence. But in general, if we think about, many of the other use cases we will share, this becomes an important part of the machine intelligence sort of ecosystem. So for me, when I think about machine intelligence, I think about the ecosystem of, this whole thing that involves, observing, that is the sensing process, the analysis, the interpretation, and the interaction or the generation part, all, involved in this sort of, cycle. So the examples I'm going to draw in the rest of the talk are, one of the domains that inspires me a lot is human health and well-being across the lifespan, right? When you look at, conditions across lifespan, early development to later in life, there are many health conditions that manifest themselves as differences in how people communicate, interact, and so on. And hence they have been sort of used either as markers for phenotyping or stratifying, diagnosing, or also looking at markers of sort of improvement or disease progression and so on, right? Whether it is autism spectrum disorder, regardless of the etiology, whether it's neurogenetic or neurological or otherwise behavioral. And so the question is, how across these various conditions, can we use rich biobehavioral information just in time, regardless of the constraints of, space and time, where you are, right? For example, someone having an anxiety attack, right, may happen in a location. They may not be necessarily close to a person that can support them, let alone a clinician. So can these kinds of, technologies be of use, right? That's something that we can imagine. So these are the questions that I think about. So the next sort of, part of my talk, I'll just pause here for a moment. I'm going to sort of, use highlights from 3 different areas to illustrate these various facets of how multimodal machine intelligence can be of use. So let me pause here and see if there's any questions. So I can't see the chat box. So if anyone has any thoughts, that they have to shout it out. All right. I'll take that as everything's all right, and then I'll keep moving. So I included the slide on, speech science because I know Ohio State has a rich history in, in linguistics and speech science. So I thought I would use and show how multimodal sort of, signal processing and machine intelligence can be of some use here. And so everything from scientific discovery to sort of applications that have clinical importance. And so let me illustrate. So one particular aspect of that. So in my lab, we've been very interested in this vocal instrument, the one that I'm using to talk to you all now, and to see how multimodal methods can help understand the structure and function of this human vocal instrument, just like we're playing sort of woodwind instrument of some sort, right? In speech science, right, there's been a long history of use of technologies for acquiring data, analyzing, modeling data, and applying using this data. So in fact, if you look at the history of development of signal processing and machine learning from statistical to current day, always they've been running in parallel, and it's very interesting. But it's not just the analysis and modeling part, but even the acquisition from X-rays to speech recordings to current day instrumentation. So it's a very interesting sort of code development, I would say. And one of the technologies that I've been particularly very interested and fascinated by over the last 3 decades has been magnetic resonance imaging. Basically, it relies on the hydrogen content, the water content in the tissues, and the differential water, hydrogen content, the protons. They're excited by the magnetic field. So the concentration of that, when appropriately sort of excited and released, will help us image the underlying tissues, right? It's a several Nobel Prize winning technology. One of the things that we've been developing is to make this technology fast to observe moving things like the articulators of the human vocal instrument, like the tongue and the lips and other parts that we can't see, like the velum. And so this was very exciting, that the ability to sense and multimodally the dance of the vocal instrument to then apply all the modeling ideas, including contemporary machine learning ideas, to understand what are these what are the principles or mechanisms behind the planning and production of speech, right? So I'll play this just to illustrate what I'm talking about.
When the sunlight strikes raindrops in the air, they act as a prism and form a rainbow. The rainbow is a division of white light into many.
So you can see, right, how intricate these movements of the human vocal articulators are, lips, and they're all moving in a very coordinated fashion. And these are done in a planned way while people are speaking or interacting. And so it provides a window into understanding the cognitive representations of language and so on, right? So it's and now you can also imagine, like, that fast forward, right? Once you have data, people that are particularly the current day AI researchers and students, right? Well, there's audio data, there's language data, there is visual video data. Well, people can think about modeling them and trying to understand representations that are meaningful, synthesis, etc. Right? So so we've been working on this technology for a long time to make it like a more improve the resolution, both spatiotemporally and and right now we can get over like 100 frames per second, far more than what is needed to sample human vocal movements, which are more around 12 to 15 frames per second hertz. And so this was made possible both with hardware and sort of algorithmic improvements, including sort of advances in machine learning and signal processing, like compressed sensing ideas. And so this enables us that ecosystem I talked about, right? One part of this machine intelligence ecosystem, that we are able to sense and process information about phenomena we want to study. Once you do that, over here.
When the sunlight strikes raindrops in the air, they act as a prism and form a.
So we can image children, we can image all kinds of people. In fact, we have just set up, thanks to NSF, a scanner that focuses on this dynamic imaging right here. And we can apply many of these advances that are happening in machine learning, multimodal imaging to optimize and design how we can acquire these images in optimal way. So that's a separate talk, but I just want to point out that part is also sort of supported by these advances in signal processing and AI. But I'll more focus on how we can analyze. So once you have this kind of technology, we can actually generate data that's of interest, or linguists are interested in looking at, linguistically rich, phonetically rich, speech samples. One of the famous databases from that kind of catalyzed many early advances was the TIMIT database, and we have a articulatory version of this corpus. So a lot of from 10 people. There's like databases that have expressive speech, emotional speech production. We have like 75. The most recent one is the 75 speaker speech MRI database. So all this I'm mentioning is that provides us information about an important aspect of human facilities, the ability to plan and produce speech. Now we can approach it with many data-driven methodologies to analyze, understand, both from a scientific perspective, and also if any of these subsystems involved in the production of speech, right, from the neuro systems to the motoric systems, the social systems, right, what happens. And we can do this both with observation, real observation, but also with these models, these multimodal models that people are, big models we're all working on, right? And so I'll just illustrate some of the possibilities, right? Analysis, one of the things machine intelligence is very useful for is to try to process, analyze, and draw inferences from these images. So image analysis, like one of the things that in vocal data are to look at these structures that are specific structures that are involved in creating these movements that help us produce the sounds that we interpret as spoken language, right? And so characterizing, for example, the vocal tract morphology, how are the vocal instruments of different people similar or different? How does it impact the sounds that they produce? How can we use this kind of information about the production to improve technologies like speech recognition, automatic speech recognition, speaker recognition, etc. Right? So
this was easy for us. Jane may earn more money by working hard.
So segmentation is an interesting problem. Again, we can approach this. Traditionally we did it with more traditional signal processing. Fast forward, we can apply novel machine learning sort of ideas. Here, this is a convolutional LSTM. This is already dated from 2020. But just to illustrate that we can use context now from long-term context and train these systems to improve the segmentation of this airway movement. Once we have that, we can then derive features that are linguistically meaningful. For example, if you are a student of articulatory phonology, like I am, then we can actually, we're very interested in the formation and release of constrictions in the human vocal tract. It's like a beautiful control system. And then we can, once you have the segmentation, we can start deriving these and then building a model, right? If you want to go through the traditional approach.
A long beard
like that,
right?
His
chin, giving those who
so
observe
we
him
make
a
a tongue
pronounced
section,
feeling
we
of
make
the utmost respect.
with the tongue tip at the sort of alveolar ridge right behind the teeth to make sounds like or T or L, coronals, and so on, right? So we can do we can derive these variables, or we can directly use data-driven models with these image representations to fit any number of these ways of characterizing these fundamental shapes with which we compose more complex movements, right? So when you think about like things that are happening in computer vision when they study movement and so on, we can apply this to this very complex movements that are happening, right? So all these machine learning intelligence approaches can be developed and applied to study something that is of scientific importance. That's the point I wanted to make here. We can also use these kinds of data to imagine new ways of thinking about technology. For example, the problem of inversion that is going from easy to acquire audio, speech audio to these representations, using a small set of jointly acquired data, can then be used to build systems that can be of potential use and robustness. So, for example, if we have a small data set with which we can jointly observe, like with MRI, for example, we can build models that can learn the relations between articulation and acoustics. And then when you just have acoustics, right, we can actually infer these features and use those features to do some downstream tasks, right? Whether it is speaker or speech or emotion recognition or whatever. And so we've shown that this advantage happens. Now, the models that we have currently, right, especially with the increasing availability of data, allows us to explore these questions, even deeply and at a scale that was not possible before. Right? So, of course, we can study things when the underlying systems are affected by disease or disorder. So I'll just use one example here of cancer. In head and neck cancer, basically it may affect any part of the tissue structures in the head and neck area. Here, this is in the oral region, basically tongue cancer. This part was resected with glossectomy, basically, and reconstructed with some aerodynamic tissue. And we want to know how this would, how we can plan this surgery and what happens after surgery to regain function like speech, swallowing, and so on. So, and we can use imaging and machine learning actually help with this type of analysis and prediction and modeling. So one of the things that we can see, once a patient has had this, how can we first characterize, as for the analysis part, as an example, how does it affect their speech production, in a more quantitative way? So a clinician is then informed, with the science that backs. For example, we found that by applying machine learning ideas, that we can show that the fundamental patterns that a patient now has is far fewer compared to a person that did not have cancer, right? Or before pre-cancer. So we have pre-post surgery data. So those are sort of ways of we can acquire data, analyze data with machine learning, but we can also do more, right? Things underway. One of the things that we're super excited about is to actually now can we close the loop with this sort of machine intelligence ecosystem to provide support, right? Like for speech rehabilitation, for example. So we can have right now what we can think about like a patient, say we have the images, a clinician observes, particular tasks that they perform, and then they can, provide appropriate therapy. But we can also actually use this data to automatically analyze the both the movement and its consequence, the acoustic consequence, and see how we can actually target and train them. So if you have just some example just with imaging, we can then just do it with audio, right? Only with inversion. So here, this is the target. So they're trying to, the therapist is asking the patient to target this corner. Yeah. We can study other sort of, conditions like stuttering, right? The etiology is neurological. Again, does these kinds of new ways of sensing, imaging, analyzing, provide new insights. For example, in stuttering, there's a lot of competing theories of, what causes that. So there's one set of hypotheses that, thinks about this is a challenge in planning. But data like such as this, what we've collected, for example, right? The initial consonant sort of that has difficulty here. But we can see that the tongue posture, right, of the following vowel is already in place while this is happening. So this is not necessarily a planning difficulty. So gives us some ways of quantitatively approaching the underlying sort of mechanisms involved, right? Yeah. So that was highlight one. I'll pause here. So I just want to show how sort of this machine intelligence ecosystem, from sensing to analysis to modeling, can help both with answering some scientific questions, but also sort of, can be translated into applications, right? Now I'm going to like switch gear into another domain of examples, now with more sort of, again, multimodal data driven, to inspired by questions, and especially in mental health and well-being, right? Again, like, let's go back to this chart I showed you. Now let's start with that. That's something we've been talking about, signals related to speech and language as biomarkers, right? There's lots of work that's coming out, particularly recently, of sort of automating and using and quantifying information from speech and human language as biomarkers to, for screening, for diagnostics, for severity sort of characterization, etc. Right? So, for example, even in our work, we have shown, simple things that have been sort of, made possible by the advances that happens in the speech, language, and conversational sort of, machine intelligence advance, everything from, diarization, speech recognition, and so on, to compute many aspects of human interaction. Like, for example, even latency, intertopic latency. Actually, we showed that it's a very stable and a robust biomarker for measuring behavioral change in autism response to specific treatments, right? That was made possible because we could implement a speech pipeline, enabled by all these advances, right? That's one possibility. Another example is to analyze language and speech patterns, right? Using NLP and, and speech modeling to look at long-term changes in mental health states. For example, in this study, we tracked about several hundred, patients with major depressive disorder risk, and every week they will call and answer, simple questions, open-ended prompts, like how are you doing, type of a thing. So we had clinicians listen to it and assess that and see is there a state change? Do they need to see them, or suggest some medication change or other kinds of intervention, or just everything's okay. So we showed that actually automatic analysis, using these machine learning ideas of vocal markers, language markers, and so on, showed that could be a robust thing, as well as a panel of experts. Similarly, we showed that, for example, analyzing interaction during psychotherapy, which is a important point, means of helping people through through conversations, what works and what is more effective. One of the things was the perception of expressed empathy by the clinician or by the client. And so we could use that as a way of understanding the quality of, for example, a particular session, right? So all these are possible with sort of progressive advances that are happening in, say, domains like speech and language processing, enabled by these advances in machine learning and and AI. So we can think about such things, right? One way of thinking about we know clinically what construct we want to sort of try to quantify or measure. We can treat that as some sort of a machine learning, machine intelligence exercise, right? We have signals or data. We can then process them at various levels, put them together to draw some inferences. So one of the early works we did was to look at people with relationship problems. So there, the clinician, the clinical psychologists were interested in characterizing when couples had trouble in a relationship, they go to a counselor. And so they're interested in characterizing things like, their affective behavior, whether they're expressing humor or they're blaming each other and so on. These are codified in terms of behavioral codes. And then, humans sit and rate these behavioral codes, and they use that to sort of understand sort of how what therapeutic means could be supportive and so on. This is more in the clinic and in the scientific aspects, not in the real sessions. No one, they don't have the time to scale this up. Now, one of the questions we early on, like this, like almost 15, 20 years ago, we asked, well, can we at least support this automatic coding through, speech and language processing? In those days, it was all like old-fashioned, hidden Markov model-based ASR and so on. But what was very exciting was that we could do these estimates of these codes, as well as the inter-rater agreement, between experts. Right? It was great. But also, as a side product, we could also analyze it. It provided some interpretability. For example, it showed that high blame sessions had lots of, use of second person pronouns versus low blame sessions had more first person pronouns. These are kinds of things that, psychology researchers were interested in analyzing, looking at the language of sort of interaction in distress relationships and how that improves and so on. So that was exciting. So this sort of inspired people to apply and think about new computational ways of, digging deeper, analyzing better. So one such direction I'll just illustrate here is the study of sort of, what happens in the dynamics of the interaction. So the idea of entrainment. For example, when two people sort of interact, right, when they want to sort of express affinity toward each other in a more positive way, they'll start aligning. For example, two friends who have met or meeting after a long time, they start sounding like each other, laughing together, matching their words and, matching their sort of head movements and so on. So this idea of entrainment is like, is there in behavioral sciences and neuroscience and so on. So one of the questions we ask is like, can we come up with computational proxies of quantifying this and use that as sort of a feature to model or infer constructs that were there implicated, right? Like, for example, positive or negative valence in interaction and so on. So in this sort of slide now, I'm illustrating a couple of ways that we try to, for example, compute vocal entrainment, right? So we can imagine embedding vocal features. We know different ways of representing and deriving vocal embeddings these days. Early on, we did it with more traditional ways. When we started, imagine, for example, PCA type ways of embedding vocal features. Then once you have these embeddings, we can come up with distance measures that kind of give you some notion of similarity. And we can use that as a way of predicting, say, some latent mental state, right? Classic ways. Now, we can, same ideas, nothing different, but we can now think about these in terms of neural embeddings and distances that are, in that embedding space. But the idea is the same. So if we have these kinds of similarity measures and representations, then we can try to see, will these be these interpretable sort of representations and measures be useful in predicting things where they are theoretically implicated. For example, agreement and blame patterns, right? For more agreement, we would assume that there are more entrainment and alignment versus where there are more blame. Couple therapy outcome or sort of emotional bond in suicide risk assessment. These are all domains that we have looked at and showed that the ability to use these analysis and machine learning type modeling can be useful to get insights that we're not able to just get from just human annotation, right? There's more details. So of course, we can write papers about this, but now can we take this to the real world? So for example, you can imagine engineering a technology pipeline to go from human interaction to target constructs, right? Like, we've been talking about audio and speech as the example here. We need building blocks for, recording processing, detecting what speeches, recognizing what they're talking about, and then other machine learning models to figure out behavioral constructs. So we've been, in the domain of psychotherapy, colleagues, several colleagues in our lab, we've been working on this to see how we can understand psychotherapy mechanisms, for example, to assess quality across various modalities of therapy, from motivational interviewing to CBT, etc. And early work, I kind of showed this earlier, sort of looked at constructs like expressing behavioral codes like perceived empathy using speech and language features, and showed that we could get very close to human agreement of these constructs. But now we can process, several, long sessions across sessions and so on, use it for training, for example. In fact, there's, these have been sort of implemented in clinics and, in a startup that colleagues have started. And this is great to see that ideas from sort of lab and, studies can actually be translated to the real world as well. Right. Of course, this also inspires us to think about new ways of modeling and advancing computational approaches. So, for example, like we were very interested in instead of the traditional pipeline of going from speech to text to some constructs, can we do, for example, jointly model speech and text, right? Or do end-to-end models, without any transcription. So these are sort of all the ideas that were inspired by this domain, but also inspired us to think about new ways of modeling, right? As the field emerges, also will methodologies and their impact. So these are just a couple of examples. In fact, this also sort of inspired us to think about, right, if different forms of therapy, like as I mentioned, motivational tutoring, CBT, DBT, and so on, there are a lot of common factors across them. So can we again apply these, look at what is common across these and what is unique by using aspects of multitask learning, multi-level learning, how to make use of context both within a session, across session, etc., and see how we can empower this analysis of what is happening in this very seemingly simple but very complex human interaction, which is very goal-driven, and help both get insights about what works for whom, when, and how, to actually translate that to useful ways of quality assurance, training, etc. So this is a very sort of satisfying sort of outcomes from this line of work and lab. But we can take these from more traditional clinical settings to the real world, right? So in one work, I'll just give you a couple of examples. Can we do proactive sort of support? Just checking the time, doing all right. For example, like we were talking about couples and conflicts. Can we detect conflict before it happens, right? So a couple of former PhD students, now professors both, did this by putting multimodal sensors on people, like wrist-worn sensors, phones turning on when they were in proximity, getting surveys from them, but also with these multimodal sensors, right? They were able to predict an upcoming conflict as well as what the people themselves were able to say that the conflict is going to happen, right? So better than even the self-reports about their mood and quality of interaction. So that was very exciting. And this was made possible by, again, multimodal sensing, all the various, machine learning ideas, with the early days of large models with these bio-behavioral data and so on. That kind of inspired us to do a pretty large-scale study of healthcare providers whom we sort of, here the idea was to see how we can understand the competing demands that are, physical, cognitive, emotional, and social of healthcare providers like nurses and doctors in a large hospital, to see how it impacts the dynamics of, both perceived stress, their performance, and other outcomes like burnout and so on. Again, bringing this idea of integrated ways of sensing, processing, modeling, and sort of, understanding sort of in real world settings. So this was sort of, an exciting project that we did, and all these data that we have released from almost about 400 people. And so especially for those interested in, IoT sensor data and so on, there's lots of data here, both sensors on people and in their environment. I'll just mention. So what are some of the things that we were interested in doing? So for example, we're very interested in health outcomes, so sleep is an important aspect of it. So we, for example, compared how day shift and night shift people are similar or different. So we know because of the workday, night shift and day shift people sleep at different times. But even in their off days, we found that their sleep start and wake up times are all disturbed. We can dig deeper because we also had physiological data from them. We can see the circadian rhythm of people who are day shift versus people who are night shift, right? The patterns are somewhat highly variant in the night shift people, saying that this is like an important aspect of well-being. And so this gives us insight that was not there before. We can in fact go a step further for predictive modeling, right? We can see how aspects of events that are happening in their life can be predicted using physiological and behavioral signals, right? So things that positive events can increase positive affect, negative events can increase negative affect, anxiety. They impact the biobehavioral signals. So we can use these to create embeddings and, of these multimodal physiological signals and use to predict upcoming sort of positive and negative events, right? So these things are all possible. But this is not very easy. This is very studying human signals is like one of the most complex things, right? Because there's so many different factors that interplay and may have similar sort of manifestation in the measurements we make. For example, right, in one domain I alluded to earlier, like studying children and particularly children with neurocognitive diversity. There's so many factors there. Children are growing, so their age is changing, their actual physical characteristics are changing, but also their cognitive states are different. How are we going to relate which aspect is important, right? So maybe we can think about advances in machine intelligence, data disentanglement, and things that we've been studying in other contexts to shine light on aspects that are clinically important. So let me use the example of autism. Autism spectrum disorder is sort of neurogenetic in etiology, but the prevalence is like over the last several years has been increasing. It's 1 in 36 children in the U.S. are diagnosed. As of most recent CDC reports. So it's characterized by difficulties in social communication, reciprocity, and so on. And the way people characterize them is through sort of studying these behavioral aspects of language and interaction, stereotype behavior. Work and machine intelligence and the kinds of things we've been talking about be of use, right? So we can think about, many ways of helping quantify, understand the communication social patterns in a quantitative way, stratify behavioral phenotyping. We can help then track, quantify progress during interventions. So all these can be sort of translated into multimodal assessment, right, of studying language, behavior, and so on. So let me sort of, so one simple way sort of machine learning can be sort of thought about, like there are many well tested and developed, clinical instruments like for screening and diagnosis, either through parent reports or through clinical observation like ADOS, right? We can use machine learning ideas on top of that to see how we can do optimal way of combining instruments, for example, or administering these things in effective way so that can provide scale up, accuracy, etc. That's one way we can do. The other is more analyzing exactly what is happening at the individual level. For example, one of the characteristics that is often mentioned clinically is atypical prosody, right? Musicality or the way we sound. And so if you look at the diagnostic manual, right, it says, the qualitative description talks about irregular rhythm, odd intonation, and so on, very qualitative. People who study speech and language, right, they know how to translate that into signal features and then know how to use machine learning to analyze it. For example, you can look at acoustic features of, intonation, pitch and volume change, voice quality, turn-taking measures, language measures, and in fact, we found, like by analyzing such thing, right, not only of the child, but also the person interacting with the child, we can show that there's, many interesting phenomena can be observed, quantitatively, that, for example, the interacting psychologists, in interactions involving psychology and child, you see that the higher the severity, there's more international variability, the changing in strategies by the person, more latencies and the use of, pronouns. All these can be, systematically quantified. And these machine learning tools can complement the clinical observation by modeling the interaction dynamics together, right? That adds more signal information. That's one way. But we can do more, right? We can quantify some of the underlying mechanisms. For example, we talked about synchrony, right, early on. So one of the things that has been sort of hypothesized is sort of variation in the synchrony patterns in children that have a sort of clinical disposition with ASD. So you can look at look at this interaction, look at vocal features, look at linguistic features, and what are favorite representations you want, and what were favorite measures of similarity, and then you can see how, if they provide insights about the nature of the interaction as it proceeds, right? We showed that by looking at these vocal and linguistic features, we can show less synchrony in tasks that are more social and emotional in children that have the diagnosis, and these measures are complementary, providing more insightful quantitative tools for the clinicians to think about these patients that they have. Of course, like before, this also inspires computational researchers to think about new ways of modeling these interactive processes, interpersonal synchrony, for example, right? Using novel architectures and advances that we are making together in this field, AI, right? Bringing better context, new sort of architectures, conformers, various attentional sort of mechanisms. And we showed that by using both local and global context, joint modeling of interlocutors, you can capture nuances of this sort of synchrony patterns in these interactions. Again, sort of the two-way interaction between sort of application and modeling. What we did for speech and language, you can do for facial expressions. For example, early analysis showed that reduced complexity in the dynamics of facial behavior in specific regions was sort of related to sort of ASD severity. Now we can dig deeper, right? We can now look at it multimodally. What is a cross-modal coordination between face and voice, for example, right? We showed that neurotypical children produce sort of these emotional sentences with strong coordination and had differential expressions for neutral sentences with not so as strong cross-modal coordination between facial expressions and voice. But children, with ASD showed no such differentiation. In fact, this coordination was further sort of weakened when it was in a social circumstance. So systematically, we can actually start thinking about it in a quantitative way, looking at these with the support of machine intelligence tools, right? So some of the things underway in this domain are assessing language levels in ASD, using technologies. Like same thing, what we do with children can do with people that are elderly with that risk for dementia. So same ideas, again, machine tools can be used. So the final highlight, it's short, is we are dealing with all the topics that I've used as examples are very human-centered and very sensitive and domains, right? So one of the big things in our field of AI, right, people are talking about how to make these technologies trustworthy and be trusted, right? We know people are richly diverse. There's a vast amount of heterogeneity in people and their context and needs. We want to broaden access. At the same time, we also want to personalize experiences like healthcare. How do we make that? Sometimes these are conflicting sort of requirements. Some of the information in some contexts may be useful in one context and not in others, right? The knowledge of, for example, age, right? And so some of this may be vulnerable to attacks and misuse. How do we go about doing all these things? These are big open questions many of us were working on. It's a separate talk, but I just want to point this out here. But I thought so there's many elements in making this happen, to make it inclusive, make it, support privacy, support safety, etc. But I thought I'll, since I'm talking from Los Angeles, end with a more sort of productive way of using some of these inclusive technologies to shine light on inclusion, right? Like drawn from media stories, moving away from health to more social scientific questions. So one of the things that we've been working on in media, the stories we tell through media, right, across a range of domains, to entertain, to educate, and to inform, and so on. Right? There's a lot of media stories out there. So often, right, the stories are told through people, through characters, who are represented and portrayed, and often there's sort of variation, underrepresentation, and even biases in these representation portrayals. So can we actually use these machine intelligence, human-centered machine intelligence technologies to shine light on these things? So we started working on this a long time before sort of, all these this current big revolution almost 15 years ago, to see how people are seen, heard, and interact in on screen, for example, film and television, in ads, and so on. So early work started looking at, for example, how women are seen and heard, right? Applying things that we are very familiar with, like technologies you talked about, right? Using computer vision to understand, to see who's on screen, who's seen for how long, how are they heard by using speaker diarization. And this gave us a lot of very useful insights. For example, like we saw, we could quantitatively show women get only a third of the time on screen. They're heard only a third of the time. But the films that they are on, actually, it doesn't make any business sense. Make female lead stories make as much or more money. So why is there sort of this disparity if it's not an essential part of the storytelling, right? So these tools provide awareness for the storytellers to think about, like, the way they are telling the story, and making sure that there are not unconscious biases that creep in. What we did for sort of film and television, the most recent is, like, we showed, did a study on TV shows, past, and similar trends and happening across sort of, various languages too. So the most recent one is a study of TV shows in India. But one interesting thing that machine intelligence made possible, right? You will appreciate that. So I said, like, we process both audio and video, right? And one insight that wouldn't have been possible. So when no one was talking, we found that on screen, computer vision showed most of the time was males that were seen. When males were talking, of course, most of the time see males, but when females were talking, most of the time we still see males, right? These kinds of insights are possible, and that's another way we can use these multimodal machine intelligence tools, human-centered ones. What we saw with audio and video applied to also language processing. We can analyze the dialogues, the interactions, and again use advances in NLP and dialogue modeling to sort of think about how these narratives are constructed and what impact it has on people. So a lot of possibilities, again, in variety of domains. And that's one of the sort of other points I wanted to make. So this is, again, I said, like, just give you a little flavor, lots of papers. I can share these slides if you're interested in this. So in summary, human-centered machine intelligence, right, help us sort of, make decisions, take actions, and respond, especially sort of, in service of understanding, the human condition, and hopefully creating technologies that can help us. I think about it in three ways. One, experts know what to do, and perhaps these technologies can help it, create more efficiency, consistency, robustness, but also create new tools for insights that we haven't gained yet, right, for discovery. Hopefully translate them into, applications, whether it's a screening, diagnostic, interventions, or tracking response to treatment, health or otherwise, right? It doesn't need to be just in health and medicine. And so a lot of exciting possibilities, but one that we need to sort of do. As I couldn't talk in detail about the trustworthy aspects, but done in a thoughtful way together. Of course, this is very interdisciplinary, many different minds and people come together to approach these kinds of questions. And I have been very fortunate to have such colleagues and collaborators. I'm grateful to all of them, and I'm grateful to you for listening to me. Thank you.
Thanks so much, Sri, for the wonderful talk. Really exciting topics. So let's open the floor for questions. Any question from the audience?
Sure.
Yeah, we still have time, so don't be shy. Just any question to the speaker.
I was just wondering if you've looked into, and perhaps I missed this, if you've looked into looking at this affective computation on like telehealth, especially because like telehealth is so much more prevalent after COVID-19 and everything like that. But the signal is perhaps worse. Like, you have so many good sensors and everything like that in a closed hospital environment. Telehealth, you're reliant on whatever computer they have, whatever lighting they have. So just curious if there's any work in that area that you've been looking into.
That's a very good question. Thank you for that. We have had some domains and data where by need and necessity, the data came from telehealth type of platforms. And we didn't do a direct comparison of sort of, in-person versus telehealth type of treatment for specific sort of domains. But we have used data from these various modalities of acquisition, as you point out, in telehealth situation, people are sort of, separated in space. They're only co-present through mediation, the device. And so while you have access to data in ways that are different, acquisition for face-to-face, but it's not the same, right? People have studied that in communication. But we found that it's still useful for some purposes that we can use to analyze. Some of my colleagues in that startup that I mentioned, that they are doing a lot of these dissemination through telehealth platforms, and they're finding these tools and methodologies to be equally applicable and adaptive. But we haven't done the direct comparison of the effectiveness or comparison of telehealth versus in person, with these methodologies.
Right. Yeah. It's definitely interesting. Thank you.
I also had a question.
Sure.
Have you, and I know we just had, OpenAI release their video generation model and all that's very new. But I know text to image has kind of been coming out relatively a lot in the last couple of years. I was interested in wondering if, in addition to things like Hollywood and Bollywood analysis, have you considered analyzing biases with regards to generative models?
Yeah, that's a big topic, right? Like, so the question is like, biases built within these generative models, whether it is language, audio, or multimodal models. A lot of people, like, including in our lab, are looking at these aspects. They're very conditioned on the models and how they're trained. A lot of these, we don't know how they came about, right? When we did, earnestly, these were not. We thought these were large models like 10 years ago, but it was nothing, right? Training with the that it's a big research topic in itself, and also, what is this bias, right? Because what biases is also very conditioned on the perspective of the representational aspects. We can say, well, compared to this is what we expect in society, for example, right? Like, say men and women are about 50% in census. Why are like only you are seeing them, this fractional time, and then when it becomes more intersectional, saying, okay, people, bring age and skin tone and ability, all these factors have become very complex. And whose perspective are we taking under what? So it gets to be a very important question of, what these biases are, at what level, and for what purpose, right? Because, and these are questions that we have to systematically ask. I feel that, this field is open, but I do think, and analysis by synthesis, right, for people like Eric and me, speech researchers, is like a very sort of a methodology we kind of use a lot. Using these generative models, especially with their big their abilities, we can try to explore aspects of it through analysis by synthesis methodologies, analysis by generation, if you may, to explore these things that we may not have observed in data or aspects. We can actually perturb these models, maybe guided by physics, biology, or social science, to explore and see how we can build tools to, look at these questions. And I think that's a great possibility. Hopefully, some of you will do it.
Thank you.
Thank you for that question.
Any other question from the audience?
I don't mean to, bogart the time, but I do actually have one more question. I was
Sure,
just,
go for it.
you're working so much within these medical applications, but also on, all these multimodal speech synthesis, speech and vision data. Do you get, and this is more a social question, really, do you get pushback from people within medicine, perhaps from patients, or just other people in that sphere with regards to the concept of creating these technologies that can functionally monitor these patients, or having a situation where you have to aggregate the data, or finally just like if you were to have, say, a downstream model that you want to try to use in healthcare, that model then needs to be taking in data, using that data, processing that data. So is there like that social pushback? And if so, how do you sort of promote your ideas with that account?
Absolutely. I think that's also a very sort of important sort of discussion point, more than a question, I think, right? Because, as, specific technologies, not necessarily what we've been talking about, emerged, right? They have, provided a lot of benefits. Let's just take them in a field of, medicine and, healthcare, right? Whether it is, observing and doing things that were not possible before. At the same time, it's also going to reveal things that may not have been. Incidental findings are common. And the trust that needs to be built within the people, all those are concerned, right? Stakeholders, is something that, crucial as we are imagining technologies and how they could be used and misused, both, right, and abused. So my own experience, right, over the years working with, people across various domains in, health and well-being, let's stick to that, has been that, if we go with an open mind, because, and looking at the problem together rather than us coming with one thing and or the other person coming with something and you are just, so, but if we can approach the problem together in a participatory way, including the people involved, like whether it is patients or volunteers who, give their time, data, and, insights to this, right? The TILE study, for example, we studied healthcare providers, right? These are people working 12-hour shifts in very complex environments, right? And asking them to wear sensors for 3 months and, putting sensors everywhere in every ICU and their like, computers. It was like a daunting task, but the way we at least were able to approach that, we had attrition of 1%, right? And I was just amazed is that they were partners in everyone in the design of the study and also helping not only, what would they like to know about this? What are their challenges? And in fact, it scientifically, made the study much better informed, and that could close the loop. And what would they like to? How would they use it? What sense of? So that it was a longer process in a way, but it was a more rewarding process for all. Right? And so we might want to think about how do we scale this up, these kinds of experiences. Others may have had, like, people are working with different populations or different questions. May not be in health and well-being, but every time we get closer to a person, right, we are getting closer to a lot of things that you're interested in, but also may either unintentionally or access or process things that are very private, sensitive, or plainly dangerous, right? Like in terms of safety and security. So I think our feeling in our lab has been, and so that has made these collaborations and partnerships more productive and open. So able to go and set up things and collect data. A project we are working right now is on sort of exploring for biomarkers, signal markers, multimodally about suicidal ideation, right? Like putting sensors. And so these are vulnerable population, right? And how do we approach that? Putting sensors on people and making them come to do experiments, and but again, having the right colleagues, expertise, right partnership, all these things help. And it's all small, bit by bit, like labs like such as like there at OSU, others, who are all working in this area together can do this. Like I think this particular seminar is like part of this AI Institute. It's a consortium of colleagues, right? Like many questions that people are asking. This kind of partnerships and so on approaching slowly builds up, I think, the field. That at least that's my personal experience and journey. Yeah, thanks for letting me share that.
Thank you for the insight.
All right, probably we have maybe time for the last question. Anybody? If no, I'll go ahead. I think my question is kind of echoes with one of the previous audience's questions. Like general AI is kind of the buzzword today, and we talk about keep talking large language models or those diffusion models that kind of revolutionize the world already again. I'm just trying to get your opinions on, or the insights on, how this generative AI can help or on the research of, for example, human-centered machine intelligence. One way I can think of is that probably these generative AI can help build better technology or tools. On the other hand, I do see there's a possibility that we are now study like human-human communication, but probably in the near future we have these chatbots, right? Like you never know whether it's a real human or not, and then probably we're gonna have a study on the behaviors of when human interact or chat with the chatbots, right? So how the chatbots can improve the quality, the services, for example, healthcare services, replacing the real nurse, for example. So I just wanted to get your insights about this totally new stuff. Yeah.
I think we can't deny that the excitement and the and the possibilities of these large models, right? These generative models that are able to sort of capture and synthesize very rich data streams, and their impact on inference and impact on generating sort of stories, if you may. It's exciting, how we are going to use them and what possibilities. A lot of it's open, right? Because it's not just in the traditional audio, video, language domain, right? You have all these foundation models, generative modeling, including in my lab, on biosignal data, right? Modeling, ECG and EEG and physiology, movement, all kinds of stuff. And so, to what purpose? I think there's lots of questions that are everything from supporting to automation, like we were talking about, say, chatbots. Would they provide? I mentioned, right? Our lab hopes to support and enhance people's experiences. Would these be, for example, in learning context or in some other context? How is it going to be used? And then we have a lot of other adverse examples that we keep hearing, especially that makes the headlines or the news also in many of these domains. A lot of it remains to be seen, but I feel that my personally, it's a responsibility of all researchers, and us as a part of the ecosystem to think about these things as a part of our research and design, right? Not only while we are creating these models, inspired by use cases that are sort of, well-intentioned and meaningful, but also thinking about like the other possibilities, and so increasingly now people are, bringing ethical, legal, and societal implications type, aspects, and in fact formalizing that as a part of our thinking in these things. So benefits are, there's a lot of also philosophical debates that happen, right? The benefits, will it be based on that, right? That what is the status quo? Access to healthcare, for example, we take that domain, right? There are only so many providers, and they may not be available when the time of need. If that is the status quo, if some of these technologies can help bridge, fill the gap in some ways to help, triage, will that be a good case? What are the dangers of that, or the negative side? So these are all questions that we need to sort of, think through, think about, and see together. I don't know the answers, in fact, but I do think about it, discuss with colleagues, and in small ways we try to attempt to understand this. But I think it's a collective effort of everyone. But especially I feel in our field, like right now, it's our collective responsibility more than anything else.
All right. Well, thanks so much again, Shri, for giving us a wonderful talk and spending time with us. We
Thank
really
you.
appreciate that. All right. Let's thanks Shri again, and we'll see you guys next time. All right.
Thanks
Bye.
so much. Thanks for having me and spending time with me. Bye.